Hello, Calculus. We are moving on to section 3 today of our series chapters. Today we're going to talk about the integral test. First, we want to say that a series of non-negative terms, so this can't be, we've looked at some series where the terms go like positive, negative, or some where maybe it starts with some negative values, but then they become positive. Or vice versa. In this problem, we are only going to be considering a series that has all positive terms, or at least non-negative, so 0 could be a part of it. We're going to say that converges if and only if, so the only way this can happen, its partial sums are bounded from above. So that means as we add together the terms and find those partial sums, we have to be reaching some sort of a boundary or a limit. Here is a graph of the curve of 1 over x squared, and we can then take each of these as terms, plugging in 1, plugging in 2, plugging in 3, and then add those together. And as we add them together, what we would be doing is then accumulating the areas of these rectangles, and we want to see if that is bounded. Our integral test is going to allow us to tell convergence and divergence. So as a reminder, yesterday we talked about that nth term test. Our nth term test can only be used to determine divergence. Our nth term test yesterday, as a reminder, said that if the limit of the terms is becoming anything other than 0, we're going to have divergence. If the limit is becoming 0, then it's an inconclusive test. We just don't know. So nth term test can only tell us divergence. Our integral test can tell us convergence and divergence. So it's a little bit more powerful of a test in that sense. So for this, we need our sequence to be of positive terms only. So if we have negative terms, this test will not work for us. We need a sequence of positive terms. And what we're going to do is then define that sequence rule as a function. That function must be continuous. It must have positive values, and it must be decreasing at least after some point. It says for all x bigger than n, where n is some positive integer. So at some point, we need this function to be continuous, positive, and decreasing. Those are the criteria of the test. If those criteria are met, then what we can do is integrate the function, and then the function and the series either both converge or both diverge. So here is an example of looking at this sequence of terms here, then where we could bound it by a function and find that they either both are going to converge or both diverge. When we do this, we can then find a boundary for what that sum would be. We can either over approximate, having some rectangles hang over, or under approximate, those rectangles are hanging under. And this rule gives us our boundaries, that if we integrate with our lower limit changing from n plus 1 to just n, that will give us the boundaries for what the remainder is, the difference between the sum and S sub n there. So we actually are not going to be calculating those remainders too much. So we are going to be more focused on just whether do we have a convergent or a divergent series. So let's look at some examples of what you might see in your assignment with this. So let's start with an integral test problem. So in the integral test, we're going to have, that's a terrible series. I get worse as we go, just so you know. Oh, and that's a terrible infinity too. Okay, so maybe I just need to start over. Let's try this again. Okay, so we're going to go, there we go, a little bit better. Series starting at 2 and going to infinity. I'm going to do a natural log of n squared over n. So what we'd want to do is make sure that these are all positive terms, and they would have to be because n is positive and natural log is going to give us positive values after a certain point. So we are going to have positive values here. Then what we're going to do is make sure that they are decreasing. So to make sure that this is decreasing, I would throw it into a graph. So you could use Desmos to graph this. I'm just quickly going to type it into my graphing calculator here. You won't be able to see that, but I'm going to type it into my graphing calculator, and I'm going to graph that and make sure that these terms are decreasing after some point. And that is the case, that I see them decreasing there after some point. They increase for a while, but then they do begin decreasing. So we're going to apply our integral test on this. We're going to integrate from 2 to infinity using those same limits of integration as the series has. The natural log of n squared over n. We'll change them to x's. We'll make it a function of x. So x squared dx here. Now, this integration is actually going to be kind of a tricky integration for us, but it's a good review of our integration techniques. We're going to do a u substitution here. So for my u substitution, we usually want to think about finding a composition and an inside. So I'm going to let u be equal to x squared, and I'm going to make a substitution. So we're going to have the natural log of u over x, and then du would be 2x dx. So dx is du over 2u, and so du over 2u. Oh no, sorry, over 2x. That's my mistake there. Let's see, fix that, d. There we go. So now I'm going to ignore the limits of integration. We could swap them out and change them from u's to x's, but I'm just going to hold off and let them just stay as they are for now, and just not write them. And in the end, we'll come back and plug those in. So when I clean this up a little bit, I'm going to have 2x squared on the bottom there. But x squared, we already defined that as u, so that was actually something we already defined. So now I'm going to say the natural log, and that's over 2u. But I still cannot integrate this. So we're actually going to need to do a second substitution. So now I'm going to let, well, we can't use u because we already used u, so now I'm going to let v be equal to the natural log of u. Then dv is going to be 1 over u du, and du will be u dv. Careful with your v's and your u's because they could start to look a lot alike. So that numerator, that's v over 2u, and then du is equal to u dv. So then I can cancel off those, and now I've got 1/2 of the integral of v dv. So I get 1/2 of raise the power and divide by the power. So I end up with 1/4 v squared is the answer to that integral. So now I'm going to start plugging things back in. So that would be 1/4 of the natural log of u squared, but then that would be 1/4 of the natural log of x squared, and that's squared, and then we were evaluating this between 2 and infinity. Now we can't technically plug in infinity, so we need to take a limit as b goes to infinity, and we're going to take b and plug that in, minus, take 2 and plug that in. And now when we think about letting b become very large, we square it, it becomes very large. Take a natural log of very large is very large, and square that and it's still very large. So we still have infinity there, which means this diverges, which means our series diverges also. I don't believe that any of the problems in your assignment are going to require you to do a double substitution like this one did, but it is a good review for us, and I do think you have a problem that will require you to do a single substitution in your integration. So in the integral test, we're going to integrate that series, and we will find whether the integral converges or diverges, and that will determine if the series converges or diverges. One other thing to talk about is something called a P-series test. The P-series test is for finding the sum of, and we usually start it at 1, but it actually doesn't have to be. It can be anything larger than 1. So 2, 5, whatever, anything bigger than 1, of 1 over n to some power. Now, we actually talked about this in our chapter on improper integrals. We looked at the integral back in that chapter from 1 to infinity of 1 over x dx. And we said, well, when we would integrate that, we would end up with a natural log. And then if we would try to plug infinity in, and again we can't, but the limit as we approach infinity, we said that that was divergent because we get the natural log of infinity, which is infinity. Then back in that section, we said, well, what about if it was x squared? We said, well, to evaluate the integral of x squared, we changed it to a negative exponent. And then when we integrate, we raise our power and divide by that power. And so then this ends up being like negative 1 over b, where b is becoming infinity, minus negative 1 over 1. And then this actually has an answer, and so this one we said converges. And we said that this is going to be the case anytime that power is bigger than 1. So if p is greater than 1, we will have convergence. If p is less than or equal to 1, we will have divergence. If p equals 1, it's actually a special name. It's called our harmonic series. And the reason why it's called the harmonic series is actually if we looked at this series starting at 1 and going to infinity of 1 over n to the first power, then plugging in 1, we'd have 1, plug in 2, plug in 3, plug in 4. As we created these ratios, what they're actually going to do is that creates the basis for musical scales and creating the notes, and so it actually does create harmonies, and that's why it's called a harmonic series. But it is a divergent series. So that can be a little bit of a shortcut, where if you have a series where we have something like, let's say, it doesn't even have to start at 1, of, let's say, 5 over n to the third plus 2, we can think about, in the end, I mean, adding 2, not such a big deal. And even multiplying by 5 won't change something's convergence or divergence. If it's divergent and you multiply by 5, it's still divergent. If it's convergent and you multiply by 5, it's still convergent. So that doesn't really change the rules of the game here. So all that matters is that we have a power equal to 3. A power equal to 3 is going to create a convergent series. Or another example, if we had a series, and we'll just start this one at 1, of 1 over the square root of n plus 7. In the end, it doesn't really matter that we're adding 7. That won't make a big difference when we're thinking about infinite values. And so we have a square root of n. Well, a square root is like a power of 1/2. So that is a power that is smaller than 1. So here we're going to have a divergent series. So look for this power rule. Now this would only work if it's just a constant number in the numerator. If there are any n's in the numerator as well, this will not work. This is only if it is a constant number in the numerator. So now you have a few different tests available to you, and your homework assignment is actually going to review all of them, which is good because this is a very long chapter. And so if we wait until the end to try to review everything, you're going to forget. So some things that you're going to be looking for in there are those geometrics that we learned about in the last section. So look for our geometric where we're multiplying by the same thing. Those are exponential in their rule. So we're looking for an exponential formula there, and then that would be a geometric series. And we talked about how those converge if our absolute value of our ratio is smaller than 1. Look for the nth term test, and I reviewed that during the notes today. And then look for times we can do this integral test, and then also look for these P series. So all of those will show up in your assignment today. As always, make sure to contact me with any questions you might have about this.